pulse width modulation regulation for the Model T. In this design I'm playing around with a component which is long forgotten. It's a programmable unijunction transistor, which was a General Electric development back in the 60s, and Philips also did their version, which they call a BRY 56. So we'll have a quick look at how it works. It's equivalent to two transistors connected thus: terminals anode, gate and cathode. And if we connect the anode up to the positive supply and have a load resistor to earth at the cathode, obviously if the transistors inside switch on, then the supply voltage will appear at the cathode terminal. Now, to get that to happen, by taking the gate terminal towards ground, base current will flow, therefore emitter current and collector current, and when collector current flows, that causes base emitter current to flow in the lower transistor, which in turn causes collector current to flow and therefore base current. So the whole thing latches up very quickly. It's just like an SCR and does belong to the thyristor family, but there's a difference in how the gate is connected. The difference is that we can actually switch off the PUT by taking the gate up to positive and therefore depriving the transistor of any base emitter current. So once the upper transistor stops conducting, so does the lower transistor, and the whole thing resets. Okay, so now to the circuit diagram. Okay, to explain how it works, usual setup that we've seen 100 times before in these videos. Generator feeds the battery through the cutout diode, and there's a shunt Mosfet which, when that conducts, that short circuits the generator and stops the charge. So in this circuit, alright, we'll assume the battery is sort of a little bit flat and the car's just being started up. So charge current flows along through the cutout diode into the battery. Battery voltage starts rising. When that happens, the error amplifier starts to operate, and again I've used a red lead as a voltage reference. So when the voltage at the wiper of the 10k pot gets to about 2 volts plus the 0.6 of the base emitter junction of the BC108, this conducts and it brings the gate terminal towards earth, which, as we see in this diagram, if we do that, that will start the chain reaction of events, and the PUT will suddenly latch up and conduct. And when that happens, we get the full supply voltage as well, maybe a fraction less than the full supply, going into the gate of the Mosfet, and that stops the generator charging the battery. Battery voltage starts to fall, red LED stops conducting, and so does the error amplifier, which allows the gate voltage to go back up to the anode voltage, which switches off the PUT, and in so doing the voltage at the 10k resistor suddenly disappears and the Mosfet switches off. Now there's an extra bit of circuitry here. I mean, for the PUT to work in this circuit, the value of the load resistor can't be too low, otherwise it becomes difficult to switch it off. In this case 10k is the value, and Problem is with that is that because of the capacitance of the gate in the Mosfet, the switch off time can be a bit slower than desirable. I have tried the circuit without it, and it does work, but the switch off time was 78 microseconds, which is look, it's probably a bit slow, but I didn't have any problem with the Mosfet overheating. But the correct way to do it is with a PNP transistor, which operates as an emitter follower. So as soon as the voltage across the 10k drops, the base of the BC557 is taken to earth through the 10k, and that presents a low impedance path which quickly discharges the gate capacitance of the Mosfet. And when the PUT switch is on, the supply voltage goes straight into the gate through the ordinary 1N914 diode there. Now, because there's no actual hysteresis in the circuit, it oscillates in the hundreds of hertz, and the things which affect its oscillation frequency is the 0.22 and the 100 microfarad and 100 ohm decoupling network is also part of the time constant, and the 270 ohm. So all these components affect the oscillation. The frequency is not critical because it's a resistive load. The point is that the switching frequency is high enough that no movement is visible on the amp meter in terms of the switching on and off. So now, quick demo. Here's the Mosfet gate waveform, and point up here is when the gate is switched on and therefore the generator short-circuited, and down here is when the Mosfet is switched off and charge is allowed to flow. There's a 5-watt lamp connected across the battery, terminal voltage 7.16. Now I'm going to put a 30-watt lamp on the battery which will exceed the charging current, and as you can see it's lost regulation, which is what you'd expect. Now take the load off, and shortly as the battery voltage rises you can see the regulation comes back in, and it's oscillating now at about 95 Hertz. If I take the 5-watt lamp off and leave the battery completely unloaded, the oscillation frequency goes down. Just move these cursors. So it's roughly about 25 Hertz, so it's still fast enough to stop any movement of the meter needle being visible. Okay, so it's true pulse width, but the frequency does vary, but as I said before, that doesn't really matter. So that's the circuit, and as you can see, the PUT is just like an ordinary transistor, 3-legged device. So this is the circuit which I'm now going to build up on a piece of Vero board and do some in-car testing.